Hello, this is Mr. McMurray, and we are going to have an electrifying time today, I'm sure. Just like we had things were really heating up last week. But this week we're going with electricity in chapter 10. All right, let's do a little bit of talking and then try to do some demos and show some things. Basically, electric charges are a characteristic of all atoms and all matter because all matter is made of atoms, and atoms contain positive charges in their center are protons, and they have electrons that circle around that. And these positive and negative charges, unfortunately, protons cannot go anywhere, so they are stuck, like on this picture here, I guess, shows down here at the bottom, just shows one proton, but the proton is stuck in the middle. All right, and they can't go anywhere. But the electrons, and they may be lots of layers, but the outside layer electrons are free to move away sometimes. And this is what allows atoms to have positive or negative charges. And in electricity, we're concerned about these electrons moving around, and that's what electricity is. Otherwise, it would be called a protonicity or something like that. Okay, it has to do with this movement of electrons. Okay, we're going to talk about that now. Basically, electricity and magnetism are like that. They're like you have one, you have the other. Okay, electromagnetic waves like light and so forth. We don't think of them as magnetic or electric, either one, but there are actually electromagnetic radio waves, microwaves, infrared, visible light that we see, X-rays, gamma rays that turn Bruce Banner into the Hulk. All of it are electromagnetic. And so electricity and magnetism go right here. And we're going to talk about magnetism and how it relates to electricity more in the next chapter. But one of the things that they have in common is that just like with a magnet, all right, if you have a magnet, it will have poles, okay? Instead of charges, positive and negative, you have north and south poles. But same thing, if you get the right opposite sides together, then I have these two that look like coins here. Okay, and I get them together, and boom, they stick together. Why? Because opposites attract. North and south poles attract. In electricity, positive and negative charges attract. But if I flip one over, so now we're sticking a north pole with a north pole or south pole with south pole. I really don't know which is which without a little magnet meter. But now if I try to stick them together, they do not want to do it. In fact, if I let go, it will repel, okay? And no matter how hard I try, I cannot get them to stay together. Okay, if I let go, then it actually flips. It repels one side and it causes it to flip over. So now they're opposite and they stick to each other. Okay. So same thing is true with electrical charges. If you have positive and positive charges, they repel each other. If you have positive and negative, then they attract. This is what holds atoms together. You got protons in the middle, electrons around it. They attract. But as you get on the edge, they're not as strong because they're farther away. And because of the distance between them, then you can actually count the inverse square law. As the distance between them gets bigger, it squares how much weaker their attraction is for each other. Okay. Now, I'm not going to go over all the atom stuff that gets in it. Just keep in mind that all electrons are equal to all their electrons. I can take an electron from one atom, hydrogen. It's not a hydrogen electron, it's just an electron. And if I stick it in another atom, it becomes that kind of electron. Protons, electrons, neutrons, the parts of an atom, they do not have identity as far as certain kinds. They're just electrons or protons or neutrons, and they're interchangeable from one atom to another. And so we have what we call conservation of charge. We don't create or destroy. They can be moved around from one place to another, and electricity is going to do that. But it does not, they don't get destroyed or go away. Okay. Now, real quickly, this is not a good thing for a demo, but I'm going to do it because I think it's important to talk about it a little bit. If you remember our gravitational formula, we had a formula for gravity, and it was Fg equals gravitational constant mass of one object times mass of another object divided by the distance squared. There's a similar formula right here for electrical force, okay, the force of electricity. Instead of G, we have K, which is an electrical constant, okay? And you have the charge of one object, which is Q1. Just don't go with the flow here. Don't worry about why it's a Q. But Q is the amount of charge that one particle has, and Q2 is the charge on another particle. If we multiply those to each other, the bigger the charges, then they will give you a bigger electrical force, okay? Just like the bigger mass will give you more gravity, all right? Over distance squared. So the farther apart they get, if just like these magnets, say they're electrical charges, if they're twice as far from each other, they're here, and then I move them twice as far, they're only have 1/4 as much attraction. That's one reason why you have to get them fairly close to each other before they will either repel or attract them. Why? Because as distance increases, the square of that distance, 1 over the square of that distance, is how attractive they are. So if they're twice as far, you get 1/4 as much force between them. Okay, if they're 4 times as far, you get 1/16 as much, and you get the idea. 5 times as far, you get 1/25 as much. That is correct. Okay, so inverse square law applies. Now, the other thing I want to talk about is Q. I don't want you to memorize this, but if you remember G, the force we multiplied times gravity was like 0.00011 zeros or 10 zeros and a 6. 0.00000000006. Okay, K is 9 times 10 to the positive 9. So this would be like 9 trillion, I believe that is. 9 trillion times whatever this number is here. So electricity is a much stronger force than gravity. Gravity is so weak, the only time you feel it is if you have something big like planets and moons and stars and stuff like that. Then you can actually feel or observe the force. But you get next to a big semi-truck, they're not big enough. Neither you nor semi-truck are big enough to exert much force because you multiply times the gravitational constant, which is times 10 to the negative ninth. Okay, so it's going to be a very small amount. It only works for very big things. Electricity is about 20 powers stronger force, and so even little tiny things like electrons and protons, which are submicroscopic, still have a strong enough force to hold every atom together in the world. Okay, so it's very strong force. Electricity is very strong. Okay, and that is Coulomb's law. It was named after a guy named Coulomb. I believe he was a French scientist. Okay, so anyhow, now also unlike gravity, gravity can only attract things. Electricity can attract things or it can repel things. Okay, once again, because if they're same charge, they repel. If they're opposites, they attract. Kind of like some people, but I don't know if that works for everybody. Okay, but anyhow, that's the way it works for this. All right, now, balloon is trying to get away from me. Okay, to have a balloon. If I were to rub it on my hair, oh, that's right, I don't have any hair. But if I had hair, okay, and I rubbed it on my hair, all right, I would actually rub off electrons, which would give it or rub electrons off my hair onto the balloon, and that would give the balloon a negative charge. Why? Because it was neutral. Positives and negatives were equal. But now I've rubbed off electrons off my hair, and so it actually has more electrons, so it has a negative charge. And so things can actually get a charge by gaining electrons, or technically by losing electrons. If they lose electrons, they're going to be positive charge. If they gain them, they're going to be negative. All right? But there's another way that something has a charge. All right, let's say we have a wall over here, and it has 6 positives, 6 negatives charges. So that makes it neutral. And normally they would be all mixed together. I don't have a before picture, okay? And all the pluses and minuses would be extra. But if I bring the balloon over and it has negative charges on it, it's going to repel the negative charges here and attract the positives. So now we have we could say we polarize it. You have a positive side over here, or pole, and you have a negative side or pole on this side. So we have polarized the charge, and this is the balloon, which is negative, and the wall charges over here are more positive, so they're going to stick to each other. Okay, I tried it in this room, but I couldn't get enough of a charge to do that. Okay, probably because of the hair thing. But anyhow, notice that the wall is still neutral. The net charge, it still has 6 positives, 6 negatives. Now, keep in mind, in atoms, we're talking billions of atoms, but I couldn't draw billions of pluses and minuses. Okay, so the wall is still neutral overall, or the net charge, the total charge of it is neutral, but it has a positive side and a negative side. So we say we have induced or forced it to have a positive and negative charge, and they're on opposite sides, so sometimes we say they've been polarized. Okay, so polarized or inducted charge means that you don't have more or less electrons. You still have the same number of positive and negative charges, but you've rearranged them so that one side is positive and one side is negative. Okay, and it's going to happen to objects. This can also happen to little things like atoms and stuff, which we'll talk about next semester if you're fortunate enough to do that. Now, this kind of electricity, like these electrons that are just sitting on here, are not moving or flowing, so we say it is static. Static means it's not moving. So static electricity, when you have your pants stick to your leg or your dress sticks to your leg in the mornings when you get up, that's because of static electricity. We call it static clinging, but that just means you have charges that are being attracted to your leg. And so it's electrical charges, but they're not going anywhere. Okay. And so they're called static electricity. When you rub your feet on the ground, in your socks, you build up electrons. Then we touch something, you feel the shock. That was static electricity that built it up on your body. Now, once you touch something, it flows into that object, and so it's not static anymore. Okay, but that's one way to get a charge. All right. All right, so let's talk a little bit about some static electricity real quick. Okay, this is, as you can see, a bottle, flask with two, I don't know if you can see it very good, but there's got little silver foil things there, and it's attached to this metal rod that sticks out the top like that. Okay, now I'm going to scoot this out here maybe so you can see it a little better and I can set it down. All right, now if I rub this plastic rod with flannel, it will rub off electrons. And when I touch this, what happens? Okay, oops. You will notice that you see those little leaves inside of there start to move a little bit. Let me see if I can get a little bit better this time. And it kind of moves out. Okay, you see they move apart. They move farther apart. Okay, and if I were to touch this, theoretically, they're supposed to move back together, but this one actually has stuck to the side of the wall. That happens sometimes. Okay, there we go. Now they're sitting there. Okay, so let's try this again. All right, so I'm going to rub this, get some more electrons on there, touch it to the top, and boom, you can see they start getting farther apart. Okay, and I move it away, and they go back together. What happens is I rub off electrons onto the rod. When I get near to this, electrons jump on there. They go to those two sides, and they have electrons, and so they're both the same charge. So they repel each other and go off to the side. Okay, and so that would be an example of where you actually have a charge where you increase the number of electrons. Okay, and they repel each other because of that. This machine is a Van de Graaff generator. It also generates electrons, but it does a bunch. The problem is it works better when it's not very humid outside, and we have a cool front coming in, and we're going to have rain tonight, so the humidity is probably going up, and it doesn't work as good. Just like static cling, it happens more when you have dry air, and it doesn't work as well at night when it's usually lower, higher humidity and less dry air. But you have a belt in the middle of this that goes around and around. At the top, you have a roller that takes off electrons, and then it has a little wire that runs those electrons up and gets on the ball up here. All right, at the bottom, it has the roller is made out of material that puts on electrons. So it puts on electrons, takes them off up here, and it builds up electrons up here. All right, so if I turn this on, then and turn it up so it goes fast enough. All right, and we turn it up, and I can kind of feel the hair on my arm stand up a little bit, but it's not very much. Like I said, the humidity has gone up so much that it doesn't work very good. But you can actually get little sparks of electricity going off. Sometimes they put these high tins on top. Electrons will go into them, and they will start repelling each other, and they will go shooting off like so. But like I said, it's not very humid tonight, and so we're having a hard time. Or it is very humid, so we're having a hard time getting much. But that's the same thing. It's generating electrons up here, okay? Once you do that, you can get a lot of neat things out sometimes. Try to repel. Oh, there we go. Now we're getting some. Okay. You can hear that. I'll pop it. All right. Oops, no, that's too much. Okay, so let me get the thing here, and I'll turn that off. But wow, there's some serious popping going on there. I don't know if you can hear that, but yeah, there's some good sparks. That one went all the way down to my feet. That one popped me on the nose. Okay, but that's basically what it's doing. It's building up a lot of electrons, okay? And so it's creating static electricity. Now, static electricity was one of the first things discovered. Benjamin Franklin had machines, not exactly like the Van der Waal generator, which is what we just did, but that made static electricity. And it was kind of like a magic show. Ooh, that's neat. Ooh, those sparks. Ouch, hurts. Pop on my nose, whatever. Okay, and so it was cool, but it wasn't really useful. Okay, until we could make electricity flow. And when we can make it flow, then we have electrical current. Okay, and we could do something besides stick a balloon on a wall or get little sparks shooting off the top of that. If I was trying to run my cell phone off that, it would be pretty hard to do much with that. So we needed some way of flowing it. Okay, and it turns out that electrons especially the outside electrons, the ones that are way out, especially as atoms get bigger, the ones out on the edge are really far from the proton, so they're more likely to come off and go their own way. Now, it turns out that some elements hang on to their electrons. They don't like to let them flow, and so they do not make very good conductors of electricity, and they are insulators. Okay, plastics, for example, the rubber glove that I used to turn off the Van der Waals. Well, it's not. Metal, on the other hand, is a very good conductor. So if I touch the bottom of that Van der Waals, which is metal, it will give me a shock. Why? Because it's going to conduct the electricity into me. It's a good conductor. Their electrons move around a whole bunch, and they don't mind. They just let them. As long as they stick somewhere in the metal, then they're good with that. And so they are very good conductors and let the electrons move around a lot. All right. Now the question is, why does electricity flow? If I have a piece of metal, a rod, I can have a metal rod, but there's no flow of electrons. Why? Because, well, they're not all going in the same direction. Okay. They may be moving in there, but the electrons are going different directions. They kind of cancel each other out. So we need something that makes them flow in the same direction. Okay, just like water. Water's going to flow if you get, say, on top of the mountain, then it will flow downhill, right? Okay, well, the same thing is true of electricity. So, but we don't actually literally take it up in the air. What we do is we get a concentration of high electrons to a concentration of low electrons. Okay, it's kind of like we talked about water. If you have high pressure water over here because it's deeper, and you have lower pressure here, if you let this go, well, it's going to push the water until they're equal. But it's going to stop. And we don't want electricity that just flows for a second and it stops. That's like when you touch the doorknob after you've rubbed your feet on in the socks, all right? That's neat. It shocks your brother or sister, but it's not really useful. So we need something that will pump water back up here so it always has a higher pressure over here than it does over there, and it will continually keep flowing. Okay, so we have to have something that pumps it back up there. Or in terms of electrons, sometimes we think of battery kind of like this little escalator auger thing that picks up electrons and brings it up. So now it has the potential energy to fall back down and go through this. From where there's a bunch of electrons, it'll flow back to where there's less, and it just keeps doing that. And so you can think of it as like a little elevator that brings it up. If it's a 1.5 volt, it brings it up a little bit, and it has it. But the bigger the voltage, like here's a 12 volts, well, it's going to bring it way up here, and then it's going to be able to flow a lot better. Okay, you got a lot more potential. Okay, and so voltage, and that's what we talk about the battery, how many volts it is. The voltage is a measure of the potential electrical energy. In other words, how high can we lift these so they have more potential to fall down, basically. Okay. For example, on this one over here, if we turn batteries the wrong direction, well, this one brings up the batteries, but this one brings it back down. It cancels each other out. We have one more battery that goes up, so it will at least bring them up this much total, but when you turn batteries opposite directions, they cancel each other out. Okay? You can put them side by side, but notice they still only bring them up a certain amount. So even though you have two batteries, let's just say this is 6 volts and this is 6 volts, these electrons only have 6 volts because they're all being lifted to the same height. Now, since they're sharing the work with these two batteries, they will last longer and they will bring it up to 6 volts for a longer time. All right. But we say that these two batteries are parallel. All right. And so they will not, they will only get up to 6 volts, but they will, since you got two of them sharing the work, they will do it for a longer period of time. Okay. On the other hand, if you put them end to end, where this one's stacked on top of that one, then it would be like this, where it's 12 volts. It would actually increase the voltage so that you have a bigger flow of more distance for them to flow, a higher concentration of electrons up here, and it would flow twice as much as it would over here. And that would be in series or in a row like that. But we won't worry about it too much right now, but just keep in mind, that's what the battery does. It gives it the potential to flow back down. And so it kind of lifts it up. Okay, or technically increases the number of electrons at one end. All right, now how does a battery do that? Well, let's talk about batteries for a second. All right, let me get some examples and I will be right back. All right, first let's talk about when is a battery not a battery? Oh, what? Let's talk about cells versus batteries. Okay, sometimes you will see batteries like this, which is a D battery. People call them D batteries, but some people refer them to a D cell or a D cell battery, which is contradiction in terms. It's either a cell or it's a battery, okay? A cell has one compartment full of a chemical, and those chemicals react, and that's what gives you the electrons at the bottom. And therefore, since the electrons are flowing away from it, you end up with a more positive charge at the top, which has a little bump on it, and at the bottom end, it does it. Now, if you look at it, I don't know if you can see this very good or not, but there's a bunch of chemicals that are inside of that. They're kind of gray and powdery. They'd be more black and white if it were actually wet and still productive. But obviously, once you cut into it, that doesn't do very good. And at the bottom, you have this little nail on the end of it, and that collects the electrons and carries them down to the flat bottom. Okay, and so these chemicals in there react and create electrons here, which gives it electric potential or voltage. Okay, and they get a positive charge at the opposite end. If we can find some way to connect these, it'll flow from high electrons to where there's low electrons. Okay, now that's basically what a battery does. Okay, but if it only has one chamber full of chemicals, that's a cell. Okay, so this is a cell, a D cell, a double A cell, a triple A cell. There are no B cells. Don't ask me why, but anyhow. And so those are all cells, and they all have the potential to create 1.5 volts. That's the amount of voltage that they can do. Okay. Now, on the other hand, if you have a 9-volt battery, which is these little diagonal ones, if you take it apart, you will see that it's like a little 6-pack, and there's actually, well, I don't know if you can see that there, but there's actually 6 of these batteries, 3 on one side, 3 on the other, and they look like maybe triple A's or something, very long, but longer, but skinnier than that's about this, yeah, a little bit longer. All right, it actually has 6 cells. So if it has more than one cell, it's a battery. So this is actually a 9-volt battery because it has 6 cells in it. And each one is 1.5. So 1.5 plus 1.5 is 3. And the next 2 are 3, and the last 2 make 3. So if you add that together, 3 plus 3 plus 3 is 9. Okay, so that is actually a battery. Now, this is a lantern battery. Okay, they sell for a lot of big flashlights. Usually these big flashlights, they had these before they came out with LED lights and stuff like that. And it is technically, yes, a battery, because inside of it, you'll see there's actually 4 cells. Okay, now these cells are very long, very big compared to some of these other ones. Let me see if I can get one out. Or not. It came out earlier. There we go. Okay, and you have 4 cells. Once again, 1.5 cells. So 2 of them make 3 volts, and the other 2 make 3 volts. So it's a 6-volt battery. If you look on the side, it's a 6-volt battery. Okay, now it has a lot more chemical in it, so it will last a lot longer. Whereas your 9-volt battery may not last very long because there's not a whole lot of chemicals in there. You get higher voltage, but it doesn't last as long. Okay, the bigger ones like a D cell or like these are got lots of chemicals in there. They're going to make electrons for a long time, so they're going to last a lot longer, but you don't get as high a voltage. Okay, and so there you go. But that's why we sometimes have to put several batteries together, like in a flashlight, to increase the voltage to light up the lamp. All right. Okay, so that's battery versus it. But basically, that's what a battery does. It builds up negative charges at one end and more positive charges at the other. Then if we connect those with the wire, we make a circuit, and that gives it a path for the electrons to flow through. And in order to flow, it has to be a complete circuit. Because if they start flowing, well, eventually you're going to run out of electrons unless they come back and keep flowing around and around and around. And that's the battery's job, is to create more electrons at one end so that they'll always keep flowing back around. They'll leave there and come back and keep doing that because they keep concentrating them at one end. But it's kind of like a pump. Okay, that's pumping the electrons or electric energy in there up in the air, so it'll fall back down or flow back down to the other side. Now, as long as you have a complete circuit, that will work. But if there's a break in the circuit, then it will not work. So, for example, here we have a little tube, has some lights in it, and it has a battery at one end. I can't really see that, but it's in there. A little flat battery, like a big watch battery. Okay, now, if I touch this part, which is metal, and I touch this part, I complete the circuit, and electricity flows through it, and it makes the lights go on and the sound go off. Okay, so that is a complete circuit. If I drop my hand, then it doesn't. Now, I could hold one end of it and then grab hands with somebody else, and as long as somebody grabs on the other side, it completes the circuit, and it will flow through there. Okay, another similar kind of thing is this, which is a ball. Notice there's 2 little metal things here. These are hooked to a battery inside, and if I connect it by touching the 2 things, then it starts to make a little noise. Okay, that one's getting to be kind of old, but I like the noise it makes better than this one. But this one does the same thing. If you touch those 2, all right, it makes the light, it makes the sound. Sounds very Halloweenish. All right, there we go. And so that is completing the circuit. So if you have a complete circuit, electricity can flow. If it's not complete, we call it, well, first of all, it's closed if it's complete, and that means it can flow. If it's open, that means there's a break in it and the electrons stop flowing because it can't go unless it's a complete closed circuit. Okay, now to check that, for example, I have this. This is a circuit tester. Okay, it has two probes in it, one to go in each side. You can stick it inside of an electric socket, unlike a fork. Well, actually, you can connect a fork in there if you want to, but bad things will happen, of course. You'll be electrocuted. All right, so basically, um, we can use these to test to see if there's a good circuit in here. If I stick them in here, it should turn the light on. I don't know if you can see that very good or not. If it does, then that means yes, it is a complete circuit and it's good to go. If I plug something in here, it doesn't work, well, I can stick this in here and find out if the reason is because the circuit's messed up. If the circuit's messed up, I need to go in there and rewire it or something. If it turns color, bright color, then I know that the circuit is okay. There must be something wrong maybe with my appliance or something like that. But this part is A-okay. All right. So one of the things that affects how much current or electric current is flowing through a wire is the amount of voltage, okay? It is also affected by the amount of resistance. Resistance is like friction, electrical friction, okay? In other words, as it moves through the wire, it rubs through things and it creates friction. The more friction there is or more resistance, the harder time it has going through the wire, and therefore you have less current, okay? And so Georg Ohm came up with a formula for that. He's the one that we named ohms after, which is what we measure resistance is. And basically, his formula says that the amount of current depends on two things. One, voltage, and voltage goes on top, so that means the more voltage we have, the bigger the voltage, the more current we can have. But it's divided by, and on the bottom, resistance, which means it's inverse, which means the more resistance we have, the less current can go through. Okay, more friction, it won't let it go through, then we're going to have a problem with that. Okay, now we measure volts in voltage. We measure resistance in ohms. Looks like an omega or upside down horseshoe symbol there. And current is measured in amps or amperes. Technically it's amperes, but we usually just call it amps for short. Okay, but it was named after a guy named Ampere, and so that's why it's actually ampere. All right, and you can see what some of these resistors look like. Usually a little ceramic thing with two wires on each side you hook the wires to, but they can be all these other different shapes, sometimes little Coke can looking shapes and stuff like this. Okay, and their job is to increase resistance. Anything electricity goes through has resistance. The wire it goes through has resistance. The battery may have a certain amount of resistance to it. The light bulb or anything that goes through to light up or appliance that you have has a certain amount of resistance in it. Okay, and so that resistance, usually we're trying to get the resistance lower so we can get more current going through. But sometimes, like say in your computer, you don't want 120 volts going to every little part of your computer. Some of those little parts just need a little bit of electricity. So there will be resistors in there that slow down the flow so you get less current coming and they don't fry the insides of your computer or your cell phone or whatever like that. So resistors help us to control how much current. We don't get too much, or if we're trying to get as much as we can, whatever. But resistance is going to do that. Okay. Now, good question, real quick. Is it more dangerous to get high current or high voltage? Okay, well, technically, it's the amount of current that kills you. Okay, but obviously, since the more voltage you have, it's a lot more dangerous to be around high voltage wires. You see signs that say caution, high voltage. Okay, because if you have a high voltage, then it's more likely. If you have low voltage, obviously you can't have too much current, probably. Okay, if there's any resistance at all. But resistance, it depends on the amount of resistance. You can have a fairly high voltage, but for example, if your skin is dry, you have like 5,000 ohms of resistance. On the other hand, if your skin is wet and salty, you may only have 100 ohms. That's the 5,000 times difference in how much resistance your body has, okay? So it is technically the amount of current that goes through your body that's dangerous or not. But obviously voltage is going to affect that, but so is the resistance. So it just depends. If you have a high voltage, but you also have a high resistance, then it may not be harmful. It also depends what part of your body it goes through. Your heart obviously runs on electricity. That's what makes it beat. So that could be a really serious thing. But it depends where it goes through at your heart, or through an arm or leg or something like that, which might not, still not be good, but would be less dangerous. Let's talk about circuits. Okay, circuit we said is the path that the electricity flows through. In this case, we have two batteries. They are in series or in order like this, and so they add together. This is a D cell. This is a D cell. So 1.5 volts, 1.5 volts. So the total voltage is 3. They add together. Remember, if they were side by side, parallel, then you would just get 1.5 volts, but it would last for a longer period of time. Okay, it wouldn't give you as high a voltage, but it would last for longer. Okay, but in this case, we're going for the maximum voltage, so it's going to be 3 volts. All right, and we have wire that can travel through, has a light up here at the top, and then it comes back through over here. Now, this is a switch. Now, you have a light switch, you have other kinds of switches. Basically, their job is to open the circuit and turn off the electric current, or to close it, and it allows it to flow through. So if I close the switch, it's called a knife switch because it looks kind of like a pocket knife where the blade comes out. Okay, if I close this, all right, it turns on the light, and there we go. All right, now say we wanted to take this off now. So basically all 3 volts is going to that one light bulb, okay, and we would divide that by the amount of resistance of the light bulb, which I don't know off the top of my head, and we would say that, okay, that is the we can figure out how much current is going through it. Now, but if we put another light bulb, now we have 2 light bulbs, okay? 2 light bulbs going through here. So it's going to go through this light bulb. Notice there's still one path. So this is what we call a series circuit for the light bulbs. Just like these are in a series, the batteries are, so are the light bulbs. They're in a row, okay? There's only one place for the electricity. So we still have 3 volts going through here, but notice that the lights are much dimmer, okay? Why? Because that 3 volts now is being shared between this light bulb and this light bulb. So really, they're only both getting 1.5 volts. And you have twice as much resistance. You had the resistance of this light bulb. Now you got the resistance of this light bulb. So that's increased the resistance. And every time we add a new light bulb, it increases the resistance. So basically, we've doubled the resistance, and we've halved the amount of voltage. Well, voltage is what increases the current, so if we halved it, that decreases it, and we've increased the resistance, so naturally we're going to have less lights, okay? And if we do one more time, let's just put a third light in there, just to make it difficult. All right, we put 3 in there, so it's still a series, one path that has to go through that electricity. Now, the light bulbs hardly, you can barely see them glowing a little bit, okay? Why? Because they're sharing the voltage, they're splitting it up, 1 volt, 1 volt, 1 volt, okay? And you have 3 times as much resistance for them to go through. So between sharing the voltage and they share equally, unlike brothers and sisters sometimes, they share equally, but they have to share it, and you also have more resistance. Each resistance adds up to more and more, and so it's like, oh, well, that's kind of a bad thing. Okay, now another problem with series circuits is if one of these burns out or gets loose, for example, they all go out. That's hard to tell that because they're so thin. They're so dim, but basically if one goes out, they all go out. If you have light bulbs like this in your Christmas tree, all right, if one bulb goes out, you don't know which of them went out, so you have to replace each one and see which one finally makes the whole string of lights, or sometimes it's only half of a string of lights, but it's almost easier just to throw the light bulbs away and a string of light and go buy some on sale at the end after Christmas or something. Okay, anyhow, but that is a series circuit. Okay, now we're going to leave the batteries in series, so we're still getting 3 volts, but now we're going to do something different. Now we're going to give the electricity alternate paths to go through, so it doesn't have to go through the same place every time. Okay, so, all right, we still have the electricity coming from there. All right, so we still have 3 volts. Okay, but now the electricity, let's try to get this where you can see it. Okay, has some alternate paths. When it comes up here, it has to go through the batteries, come around here through the switch. Okay, but it can go through the middle one, through the bottom one, or the top one. And now, so it's kind of like having a 3-lane highway. If you have a highway that only has 1 lane, and all the cars have to go through it, what happens? Well, traffic backs up because there's a lot of resistance. It's hard for them to all fit in that one path. But if that 1 lane goes to 3 lanes, now it's easier for them. They can pick which path they want to go, and they go the easiest way they can, and traffic will go a lot faster when you have 3 lanes open. Okay, so let's see what happens with our lights when we turn them on. Okay, so we put our switch down. And now good. I'll make sure I had it all connected right. Okay. And notice that all three of them on. And are they bright? Yes. In fact, they're all just as bright as when we had just one bulb in the series circuit. Okay. That means that each of these bulbs is getting 3 volts. Okay. Now, if these identical bulbs have exactly the same resistance, then they will also have the same current because they're getting the same voltage, they have the same resistance, and you end up with they're all getting the same amount of current. Okay, instead of splitting it between the 3 like we did on the other ones, now they're all getting the full amount. So I said, well, that's good. And there's some other advantages. If one of these goes out, well, that means electricity can't go through the top path anymore, but it can still go through the other ones, and you'll notice that they're still just as bright as they were before. And when I screw that one back in, it doesn't affect how bright they are. Okay, so they're still getting the full voltage. Okay, and if they have the same resistance like this, they're also getting the same amount of current. All right. Now, let's try one. Like I said, it's nice that they don't go out. Let's try something else. Let's say on this bottom one, I change it a little bit. And instead of having 3 branches, I'm just going to have 2 branches. But on one of those branches, I'm going to have 2. Okay, let me see if I can get this right and get it set up right. Okay, so when the electricity comes over here, whoops, sorry. When the electricity comes over here, it can go on this top branch, which only has 1, or it can go on the bottom branch, which has 2. Now, let me see if I did that right. Okay, I did. All right, now notice something. Each branch, the top branch and the second branch down here, both get 3 volts of electricity. But on this branch, you have twice as much resistance because there's 2 bulbs on it, and they're in a row, so it's like a series. It's like a series circuit inside the parallel circuit. And so even though this branch gets the same amount of voltage, you have double the resistance, and so you have less current going to these 2 light bulbs. And so these 2 light bulbs have less, and so that's why they're dim, kind of like a series circuit. Okay, if one of these goes out, guess what? The other one goes out, but it doesn't make the one up here go out. Okay, so anyhow, you can have a series on one of the branches of the parallel circuit. Keep in mind that each branch still gets full voltage, but you have more resistance now, so you have less current going through this one. All right. Okay. So anyhow, that's kind of what we want to see with that. Now, question is, what kind do we have in our houses? Do we have series circuits or do we have parallel? Well, if we were series, if one light bulb went out in one room, all the other ones on that circuit would go out as well and would not work. That would not be good. Also, every time you plug a new one in on that series, it would divide the voltage between however many new things you have plugged in, so you get less and less voltage, and eventually things wouldn't work. So we do not use that. We use parallel because you get the full voltage on each branch. So every outlet in your house has the same full 120 volts. Okay, or they're about 112, 120, somewhere between there, depending on various things. But okay, so that's great. But there's a downside. There has to be a downside, right? Because it has to do with power. You have to pay for the electrical power, and power is the current times the voltage. Well, on a parallel circuit, every socket is getting the full voltage, and it's getting more current usually. Okay, because you don't have as much resistance, and so you're using more power, which means that's why it's going to cost you more. Or in my little circuit with the batteries, okay, it's going to wear out the batteries faster because you can't have more light, more electricity, more voltage going to each one, and you got to pay for that, and you pay for that in the fact that it uses more power, and therefore your battery will go out and wear out quicker. Okay, and so that's the difference between a series and a parallel. But the nice thing about parallel is each time you add this, each time you have new paths, you actually reduce the resistance. You get less and less resistance, which means you get more and more current going through. The problem is, if you get too much current, it gets really hot and it can catch your house on fire. So we have to come up with some ways to help protect our house from getting too much current. All right. In your house, you used to have a fuse box, and a fuse box would have these. They have little threads on them. You would screw them in, and the wire coming in would touch on both sides to this, and it would allow the electricity to go through it. But it would have to go through. I don't know if you can see in that window. There's a little piece of strip of metal there. Okay, if too much current, too much amps is going through, it would melt that. Well, if it melts it, it opens the circuit and basically turns it off. All right. Problem was, say you did that on the weekend and you couldn't get to the store until Monday. Um, you were without electricity. So people said, since that's about the size of a penny and it's copper, I could just stick a copper penny in there and it will still work, which it would. But unfortunately, something was making it get too hot, and now you have a penny in there. That penny's not going to melt like the little wire in there would and protect your house. And so now you might burn the house down, especially if you forgot to get the fuse on Monday or Tuesday or Wednesday and let it go for a while. It might very well burn your house down. Okay, and rather than fixing whatever the problem is that's causing it to get too much current going through there. Okay, so instead of amps or fuses, now usually you have a box and it has a bunch of these. These are metal, these are black boxes, and they have a switch up here on the front. Okay, and you switch it on or off. Okay, normally it would be plugged in, and your wires would come into it, just like they came into the fuse box. Okay, now, if too much current comes through, electricity creates magnet fields. Remember, I said electricity and magnetism are like this. Okay, so if too much electricity, it creates a strong magnetic pull, and it flips the switch. It uses that magnetic pull to switch it off. The nice part is, since it didn't melt anything, you can just go flip it back on. Now, if you didn't fix the problem, it's just going to create too much current and make a magnetic field and flip it back off. Okay, so you got to fix the problem, but instead of going buying a new fuse, you can just turn it back on. Okay, and it would work. So it was a reusable fuse, so to speak. Okay, and so that was a much better improvement. Okay, we also have fuses. A lot of electrical equipment has this kind of fuse, this glass. I don't know if you can see it in there, but there is a little glass piece of metal. Here's one. You can probably broke the glass so you can see it. But basically, you'd have glass tube there in the middle. But you see that piece of wire, and so basically, depending on what amp fuse it is, if it gets more amps than that, it will melt the fuse and open the circuit. Okay. In your car, you have little pluggy ones. They used to be bigger, about like this, but most of them are smaller. I've noticed in my car now, and I don't know if you can see on that one, but there's a little U-shaped thing in the middle, but it's melted at the top. Why? Because it blew the fuse. Too much current went through there and it blew it. I was using a electric pump through my cigarette lighter, or I guess it's 12-volt outlet now. But anyhow, and it should. I don't know if you can see that one, but this one's more of a Z shape, but it's entire. The whole thing is there. If it had overloaded it, it would melt that, and that would help protect the car. Okay, so those are fuses. Another thing we have to protect against is what if say you have a appliance and you're in the kitchen or somewhere and the surface gets wet and the cord has like a little cut in the insulation, and so some of the electricity is going into the water. Okay, being conducted into the water. All right, if you stick your hand in the water, then guess what? You're going to be electrocuted. Okay, so any outlet that is around water is going to have what we call a GFCI, ground fault current interrupter. Okay, and sometimes they have red and black. Sometimes they will just be the same color as the other ones, so it doesn't show up as much. But anywhere near water, because that's where it's most likely for you to get electrocuted. And what happens is it's measuring the amount of electricity going out and then coming back in, because remember, a circuit, it's got to go through one wire of your cord, and it goes to your appliance and then comes back in the other one. All right, it monitors how much leaves and how much comes back. If there's a short and someone's leaking out into a puddle of water or something, there's not as much coming back, and it will flip it off, and you'll have to go in and hit the reset button. Okay, when you hit the reset button, it'll pop, and then it will let water go through again, electricity go through again. But if you haven't fixed the problem, it's going to pop right back off. So once again, you got to fix the problem. But once again, you can just hit the reset button. But it helps protect you around sinks and bathrooms and kitchens and stuff like that, so that you don't get electrocuted by little gaps in the insulation of the wire or something like that. Okay, so usually if it's an old house, it may not have those, but if it's a newer house, it's probably been required to put those in anywhere near water. Okay, now we're going to look at one example of a fuse and how it works, and then we will be done for tonight. All right, so we're going to show how a fuse works, also a little bit about a short circuit. Okay, normally electricity, the current goes through the wire. It goes into an appliance which has resistance, like the light bulbs on our short circuit, our little circuit here did a minute ago, or a blender, or whatever. And so that reduces the amount of current because you have a high resistance. Okay, but say you have two wires in your cord and they touch inside here. Some reason it gets cut or something like that, and they actually touch each other. Okay, now instead of going to your appliance and coming back with after it has been reduced by the resistance, now it just takes a little shortcut, jumps back here, and goes straight back to the circuit with no resistance reducing the current. So you get a high current, and it just keeps going back and back. It jumps or takes a short circuit, and therefore it's very dangerous and can build up a lot of heat. Once again, cause problems. This is also another thing that fuses help protect us from. Okay, so what we're going to do, we're making a short circuit here. I don't know if you can see it here, but I have foil, aluminum foil here, hooked onto the wire. Okay, and that's going to be our fuse. If it gets too hot and melts, then it's going to take it. It's going to melt and hopefully break the circuit so we don't do damage to our electrical system or to the school. Right? That would always be nice. I've never blown up a system yet, but we'll see. Always a first time, right? Okay, so I'm going to plug it in. And basically, it's going to be a short circuit because there's no appliance or anything to have any resistance. So if I... Ooh. Hang on just a second. Okay, that's one of the problems. With the real fuse, you don't have it attached to a balloon. But let's just plug it in and see what happens. All right. That looks really cool if you do it in slow motion. Hopefully you got that. Okay, so basically, when the electricity went through here, since there was no resistance to slow it down, it heated up and it melted the little pieces of the fuse. And it also got very hot, which popped the balloon. Now, a fuse doesn't pop anything, it just melts. Very undramatic. And we try to line it up a little bit with the balloon explosion, okay? But that's basically what it does. And so fuses are there to help protect your device from overheating or getting too high currents and doing damage to it. Okay, it's kind of a hassle because then you got to buy a new fuse or whatever, but it's really for your own good. And the problem is, a lot of times, when you plug in a cord here, that's like one of those branches of a parallel circuit, and then you have a surge protector and you plug things into it and throw things into it, and now you've got so many devices on there. There's so many pathways electricity can go through. The resistance gets really low and the current gets really high. And then that's when it blows fuses or flips off the circuit breaker and so forth. Okay, so very important that we have circuit breakers and fuses when we get these high currents that are dangerous. All right. Other than that, that's it for electricity. Stay away from high voltage. That's that my thing for you. Oh, one last thing. We didn't talk about AC/DC. Direct current is like a battery. When you plug into a battery, the electricity flows one direction. That's it. And it's AC/DC, which is a rock band. But also one direction is DC. Okay, or DC is one direction. And so it only goes in one direction. That's it. It just flows this direction. Now, it doesn't go really fast. It moves fairly slow, but as long as it's moving, it's an electric current. Okay? Now, alternating current, AC, goes back and forth, changes directions 60 times per second. We say it has a frequency of 60 hertz because it changes direction 60 times per second. Okay? So that is very, very fast. Okay? And it turns out that batteries can work with direct current, but if you try to get large amounts and send it through power lines, direct current doesn't go very far, and you can't get a very powerful amount of it. And so you would have to put a power plant every couple miles or so to a house. Okay, there'd be power plants everywhere. And when they started making power plants, Edison was in favor of direct current, although he changed his tune eventually because he realized that wasn't going to work. He quietly changed his tune, but Tesla came with the alternating current, which changes direction every 60 seconds. And you can get very high voltages, and they can go long distances because they don't lose any electricity on the way. And so a very efficient way to do it. And so all power plants use AC. So anything you plug into the outlet is going to be alternating current. Anything that uses a battery, say your phone, for example, uses direct current. Now, when you charge your phone, you're plugging a direct current into alternating current. So two things happen. One, it takes your charger takes 120 volts and lowers it usually about 3.5 volts, somewhere around 3 to 5 volts going into it, because 120 volts would fry your phone. So it steps down the voltage. That's good. But it also changes alternating current to direct current. Okay, and then it recharges your battery, which resets or undoes all those chemical reactions that produce the electrons to give you electricity from the battery. Now it resets them so that they can react again and give off electrons and run your phone off direct current. So batteries are direct current and A is alternating. Now, um, this is an LED light. All right, just one of those little lights. We have all kinds of lights in our electronic devices, little red warning lights and what have you. Okay, this is a battery. This is kind of a watch battery, so you have positive and negative sides. All right, if I put it on one direction, it doesn't work. Oh, one direction. There's that group again. It must be everybody's favorite rock sign. But if I flip it over and do it the other direction, it works. Now, normally, electricity doesn't matter which way it goes. Okay, it doesn't matter which direction it goes, right? And so if I flip the battery around, it'll just run the other direction, but it'll still make the lights work. But LEDs only work one direction. Now that's direct current. Think if this was alternating current, it would change direction. So it would go on, off 60 times per second. So if you have a flashing light, then it may be some kind of LED a lot of times in your appliances and stuff if you have flashing lights because it's going to go change back and forth if there's alternating current going through. Anyhow, just kind of interesting there. All right. Anyhow, that's it. Hope you have a good week. Don't forget, turn your questions in. Actually, make sure you have turned in your article summary, I think, if that's due this week, depending on who you are. But I think that is due tonight, possibly for some of you. And anyhow, have a great week, and don't forget to take your quiz. See you next week.